Hello, Math 157ers. This is Professor D, and this is a presentation on discrete probability distributions. Just some vocabulary to start. A random variable is a numerical measure of the outcome from a probability experiment. Its value is determined by chance, and random variables are denoted using letters like X. So what is a probability experiment? It could be the probability of getting a heads or a tail on a die, the probability of the 6 different outcomes when you roll a 6-sided die, the probability of getting a certain card out of a deck of cards or a certain type of card out of a deck of cards. It could be almost anything you could imagine. So let's keep going. A discrete random variable, it's a random variable that you can either has a finite number of possible values or a countable number of possible values. And those things aren't necessarily mutually exclusive, but the first thing I do when I'm dealing with random variables is to figure out if I can count it. If I can count it, more likely than not, it will be a discrete random variable. If it's something I really need to measure, like time, weight, height, those are continuous random variables, and they have an infinite number of possible values that is not countable. So let's look at some examples. We're going to figure out whether or not these variables are discrete or continuous. The number of light bulbs that burn out in a room of 10 light bulbs in a year. Well, there's a finite number of values that it could be from anywhere from 0 to 10. Plus, it's also countable. So this makes this a discrete random variable. In our next example, the length of time between calls to 911. Well, it's not going to be a finite value, and I cannot count it. So that it's a measurement, and that would be continuous. Last example, when a single die is cast, the number of pips shown on the die, those are the little black marks on the die, and that can be any number from 1 through 6, so that is countable, and that would be discrete. All right, to define random variables, we will use mainly capital letters like X, and we'll use small letters to list the possible values of X. So a single die is cast, again, X represents the number of pips shown on the die, and the possible values of X are 1 through 6. Probability distributions. A probability distribution will provide the possible values of the random variable and their corresponding probabilities. A probability distribution can be in the form of a table, a graph, or a mathematical formula. Important things to know about all probability distributions is that the sum of all the probabilities in the distribution must equal 1, and each individual probability in the distribution is between 0 and 1. So the question is, does this table represent a probability distribution? Well, are all the probabilities between 0 and 1? Yes. Now the second question is, when I add them together, does that equal 1? And in this case, they don't equal 1. When we add all those probabilities together, we get 0.97, which is less than 1, which makes it not a probability distribution. Second example, again, my random variable can be any value from 0 to 5, but the probability of getting that random variable looks like it ranges between 0.04 and 0.22. So the question here is it a probability distribution? All the values are between 0 and 1. There's no negative values. There's no values over 1. Now, what is the sum of all the values in the probability distribution? It's 1. So it is a probability distribution. Sometimes people do better when they're first learning probability distributions to think about them in terms of percentages. So when we talk about things, there could be like a 0% chance of something happening, which means it will never happen, or a 100% chance of something happening, which means it's definitely going to happen, or any number between 0 and 100%. So the 0 corresponds to 0, and the 100% corresponds to 1. And so you could say the 0.18 here would correspond to 18%. Okay, let's go back. A probability histogram is a histogram in which the horizontal axis corresponds to the value of the random variable, and the vertical axis represents the probability of that value of the random variable. So this is a probability histogram of the number of DVDs a person rents from a Redbox machine during a single visit. So let's look at this. So about 58% of the time, 0.58, they rent one DVD. About 3% of the time, they rent 4 DVDs. And about 6% of the time, they don't rent anything. And here is the discrete probability distribution shown as a graph. So we look, here's the 0. It corresponds to 0.06. Let's look at the 3. 3 was 0.1. Yep, that corresponds to 0.1. Which occurs the most? The 1. And that corresponds to 0.58. Now just be careful, because if we look, the values of our probability in this graph go from 0 to 0.6. So this might not be the best view of the graph. You might really want to have a graph that goes from 0 to 1. But we're still just getting the idea behind it. Now let's find probabilities on this wheel. It looks like the numbers go from 1 through 12, and I'm going to tell you that each outcome is as equally likely as another one to occur. So the first probability we want to find is that x is equal to 5, exactly 5. Well, the 5 occurs once on this wheel out of 12 attempts, so the probability would be 1 out of 12. The next probability that we're looking at is that x is greater than 7. So when it's greater than 7, it doesn't include 7, but that could include 8, 9, 10, 11, and 12, or 12. So the probability that x is greater than 7 is really the probability that x equals 8 plus the probability that x equals 9 plus the probability that x equals 10 plus the probability that x equals 11 plus the probability that x equals 12. And that's 5 out of 12 because those are 1, 2, 3, 4, 5. So 5 out of 12 times, we would expect that if we were to, roll, we had a little spinner on here, we would expect that the probability that x would be greater than 7 5 out of 12 times. Our last example is the probability that x is less than or equal to 2. So less than or equal to 2 includes 1 and 2. So probability that x is less than or equal to 2 is going to be the probability that x equals 1 plus the probability that x equals 2, which is going to be 2 out of 12, which we need to always reduce, so that's 1 out of 6. It's a different type of chart, but we're looking at finding more probabilities here. And let's just take a look. So we have male and female students, and these are the numbers. You got an A, B, and C. So we look across. We have 15 males got an A, 16 males got a B, 9 males got a C, for a total of 40 males. 2 females got an A, 11 females got a B, 12 females got a C, for a total of 25 females. So the total number of students we have is 65. Now we can also look at this vertically. If we look at all the A's, well, there are 17 total A's, 27 total B's, and 21 total C's. And if we were to add them up this way, we would also get 65. So let's look at some examples. A male student earned an A. Well, there are 40 male students, so this is really the pool we're looking at. And out of those 40 male students, how many earned an A? 15. So we have 15 out of 40, which reduces down to 3 over 8. A student earned a B. So when we talk about a student, we're talking about the total number of students. So that's 65. And how many of those 65 students earned a B? 27. And we cannot reduce that. A student who earned a C was male. How many students earned a C? 21. So that's going to be our group that we're looking at, 21 students. And how many of those were male? 9 out of 21, which will reduce to 3 out of 7. Now we're going to review some probability formulas. Probability of A and B, so when they're independent, it's simply a probability of A times the probability of B. So what are two independent events? Rolling an even number die and pulling a heart out of a deck of cards. So we're going to get probability of rolling an even die times the probability of getting a heart. An even die is 3 out of 6 because 2, 4, and 6 are all even outcomes. So you have a 1/2, it's 1 out of 2, which reduces to 1 out of 2. The probability of getting a heart out of a deck of cards, where there's 4 different suits in a deck of cards and there's 13 cards in each. So that's 13 out of 52, or 1 out of 4. So the probability of getting of A and B is going to be 1 out of 2 times 1 out of 4, which is 1 out of 8. Now, when they're not independent, we have to go into this idea of a conditional probability. But when they're not independent, it's the probability of A times the probability of B given A, where P, probability of B given A, is the conditional probability of B given A. And over here, conditional probability is the probability of an event given that another event has occurred. So here, for example, probability of getting a heart on the first draw and probability of getting a heart on the second draw given the first card was a heart. So the probability of getting a heart on the first draw is 1 out of 4. Now, probability of a heart on the second draw given the first card was a heart, there's our conditional probability, because if the first card was a heart, we only have 12 cards left in the deck. Additionally, because we have pulled a card out, right, and we haven't put it back in, there's only 51 cards left in the deck. So we're going to end up with 1 out of 4 times 12 over 51, which will give us 12 over 204, which will reduce to 3 out of 51. Now we're going to talk about probability of A or B. Okay, when events are mutually exclusive, and what does mutually exclusive means? Mutually exclusive events are ones that it is not possible for both to occur. So flipping a fair coin, you can either get a heads or a tails. It's not possible for both a head and a tail to occur. Since one result prohibits the other from occurring, one event excludes the other. So probability of rolling an even die or drawing a heart. Well, probability of rolling an even die is 1 out of 2. These are mutually exclusive events, plus getting a heart, which is 1 out of 4. Create a common denominator. I'm going to rewrite my 1 out of 2 as 2 out of 4. So it's going to be a 3 out of 4. Now, when events A and B are not mutually exclusive, its probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Our next few slides will go through a non-mutually exclusive event. And here's a great website for more examples and information. So I call this the intoxication question. You do have this on your homework. It might be slightly different, but I'm going to take you through the steps and how to solve it. So this table summarizes pedestrian deaths in 981 car accidents. If one of the pedestrian deaths is randomly selected, find the probability that the pedestrian was not intoxicated or the driver was not intoxicated. So let's just kind of look here. Driver intoxicated, yes, no. Pedestrian intoxicated, yes, no. So there were, if we add all of these numbers up, we'll see that we get 981. So when the pedestrian was not intoxicated, we would look at this whole column. When the driver was not intoxicated, we're going to end up looking at this whole column. So let's see where we go. They're not mutually exclusive, so the probability of A or B is going to equal the probability of A plus the probability of B minus the probability of A and B. So here we have the probability the pedestrian not intoxicated or the driver not intoxicated is going to be the probability the pedestrian was not intoxicated plus the probability the driver was not intoxicated minus the probability the pedestrian and driver were not intoxicated. Again, if we go through these things, we can see where the 981 comes from because we added up all the accidents, so we have 981 total. The probability the pedestrian was not intoxicated, when we look in this column right here, so that's going to be 86 plus 621, and remember we're looking at all the deaths, so we're looking at 981 as our denominator in all these questions. So 86 plus 621 gives me 707 over 981. The probability the driver is not intoxicated, I'm going to look across this way. So I've got 230 plus 621. So that gives me 230 plus 621 over 981, which will end up being 851 over 981. Now I have to look at the probability the pedestrian and the driver were not intoxicated, which is 621 over 981. Again, we just have these numbers from the previous screen. Probability that the pedestrian was not intoxicated or the driver is not intoxicated is going to be 707 over 981 plus 851 over 981 minus 621 over 981, which will give me 937 over 981. And that is my answer. The last topic here is the mean of a discrete random variable. So the formula for the mean, there's that mu we've seen before, mu sub x, I'm talking about a discrete random variable, is the sum. That's what this little symbol says, the sum of each individual x times the probability of x occurring. So where x is the random variable and probability of x equals that is the probability of observing that random variable. The expected value of a discrete random variable is computed the same way as the mean. So really, means and expected values are interchangeable. So let's go back at our DVD rental problem. Again, we have our discrete random variables. X goes from 0 to 5 and the probability of that occurring. So we're looking, here's my x and my probability of x, and I'm going to multiply my x times my probability of x all the way through. And you can see these numbers over here. So 2 times 0.22 gives me 0.44. 3 times 0.1 gives me 0.3, 4 times 0.03 will give me 0.12, and 5 times 0.01 will give me 0.05. So now I'm going to add these together, and I'm going to get 1.49. So the mean of this distribution is 1.49. The expected value of this distribution is 1.49. So we can expect, on average, that a person will rent 1.49 DVDs per visit to a Redbox machine. Now, of course, we know that 1.49 is not even in the probability distribution, but that's okay because we're looking at this expected value as what we would expect on average. And that is all I have. Hopefully you found this helpful. The slides for this lecture are available as well.